When factoring by grouping, the goal is to group the first two terms of the polynomial and find what's in common in those terms. In this first set of terms, the purple set, there's an r in common. As you can see, you factor out an r, and what's left is a plus b on the inside. In the second group of terms, sa plus sb, you factor out an s, and what's left is a plus b. A plus b is a factor in both terms. What's not a factor in both terms is r and s. So what you can do, since a plus b is a factor in both terms, you can factor out a plus b. What's left is r plus s. Think of a plus b as y. If you had ry plus sy, you would notice that y is in both terms and you can factor out a y, which leaves you with r plus s on the inside. That y in this situation was just a plus b. So that is what allows you to factor out the a plus b. Now notice how down here, a plus b was on the left, and up here, a plus b was on the right. Remember, multiplication is commutative, so it doesn't really matter which goes first. This is another example that we're going to factor by grouping. Now, just so you know, anytime there are four terms, you should look and see if you can factor by grouping. So since there are four terms, we're going to try to factor by grouping. So when you factor by grouping, you always group the first two terms together and the second two terms together, and you look for a common factor. So if you notice, in our first two terms, x squared is our common factor. And what's left when we take out an x squared is x plus 7. In our second set of terms, we notice that there's a negative 9 in common. Now, whatever the sign is here, you're always going to keep. So there's a negative 9 in common. So when we factor out the negative 9, we're left with x plus 7. Now, if you're wondering if I did that correctly, you can always redistribute the 9. So negative 9 times x is negative 9x. Negative 9 times 7 is negative 63. Now, if you look at the two terms we now have, x plus 7 is a factor in both of our terms. It's a common factor. So what we can do is we can factor out our x plus 7. So x plus 7 is on the outside, and what's left on the inside is our remaining two components that were not common. So x squared minus 9. Now the problem says factor the polynomial completely. While this is factored, it's not factored completely because we know that x squared minus 9 is a difference of perfect squares. So we can continue to factor by going x plus 7, and then x squared minus 9 factors to x plus 3, x minus 3. Now it is completely factored. Here's another example that we're going to factor by grouping. So we have our first two terms that we're going to see what's in common, and then we have our second two terms, we're going to see what's in common there. So in common with the first two terms is another x squared. So we take out the x squared, and what we're left with is x minus 3. Now, if you recall from before, we need to keep the sign in common. So we need to keep that negative sign. So what we're going to factor out in this problem is a negative 16. So we're going to factor out a negative 16, and what's left inside is x minus 3. Now we notice again that x minus 3 is a common factor in both terms. Since x minus 3 is a common factor in both terms, we can factor it out. So on the outside, we have x minus 3, and left on the inside, we have our two factors that are not common. So we have x squared minus 16. Well, it says factor completely, and we have not factored completely because this factor can be factored more. If this could not be factored more, we would be done. So x minus 3 can't be factored anymore, but x squared minus 16 is a difference of perfect squares. So it's x plus 4, x minus 4. Now we have factored completely. These practice problems have already been completed for you, so you can check to see if you got them right. But I want to point something out. In this particular problem, but when you factor by grouping, you notice that there's not really anything you can factor out of this x minus 1 term. However, you can always factor out a 1. The reason you can factor out a 1 is 1 does not alter anything in the problem. So if you factor out a 1 and then redistribute a 1, you still have what you started with. So 1 times x is 1x, and 1 times negative 1 is negative 1, which is what you started with. Now the reason in this problem why you factor out a 1 is that creates your two common factors in both terms. Your common factor in the first term when you factor out the 3x is x minus 1. If you don't factor out a 1, there's no common factor in this, there's no factor in the second term. But if you factor out a 1, you also create another x minus 1, which becomes the common factor that you can then pull out. So that is why you do factor out a 1 if there's not anything you can factor out. You have used difference of squares in the past to factor, but you've probably never used it as a pattern. This pattern can be really important in making your life a little bit more efficient when simplifying. So a squared minus b squared is the same as saying a plus b times a minus b. So if you start with 100 minus 25, these are both perfect squares. And you could rewrite it as 10 squared minus 5 squared, which you could also then rewrite as 10 plus 5, 10 minus 5. Now, if I was given this problem, 10 plus 5, 10 minus 5, instead of doing 10 plus 5, which is 15, and 10 minus 5, which is 5, and 15 times 5, which is not really something I can do in my head, it would be more efficient if I rewrote this as 10 squared minus 5 squared, because I can do 10 squared in my head, which is 100, and I can do 25 squared in my head, which is 25, and I can do that subtraction in my head, which is 75. We will use this pattern of going this way and the pattern of going this way to make our lives a little bit more efficient. We'll use the idea of difference of perfect squares to factor these two problems. So x squared is a perfect square and negative 4 is a perfect square, and there's a negative sign. So we can factor this as a difference of perfect square. So we have x plus 2, x minus 2, and we're finished. But this problem's a little bit trickier. 16x to the 4th is a perfect square, and 81 is a perfect square, and we have the negative sign, so there's a difference of perfect squares. So we will first factor 16x to the 4th. That's 4x squared, 4x squared, and then 81, the square root of 81 is 9. So we have a plus 9 and a minus 9. Now there's no formula for the sum of two squares. So 4x squared plus 9 cannot be factored more. But if you notice, 4x squared minus 9 is also a difference of perfect squares. So we can continue to factor. So on this stays the same. So we have 4x squared plus 9. But this, the perfect square of 4x squared is 2x. So we have a 2x. We have a 2x, and the perfect square of 9 is 3. So we have a positive 3 and a minus 3. That is factored completely now. We can use the idea of difference of perfect squares to simplify something efficiently. So if you notice, we have a 3 and a 3, so those are both a perfect square, and we have a root 2 and a minus root 2. So we know we have a difference of perfect squares. Remember, a minus b, a plus b just becomes a squared minus b squared. So what we can do is we can take the two terms, the a squareds, and we can just write 3 squared. And then we can subtract root 2 squared. Well, 3 squared is just 9. Root 2 squared is just 2. So 9 minus 2 is 7. And that's how we can simplify that efficiently. Now, if you notice this, we can't simplify this one easily right now because we have 2 minus signs. So there's no difference of perfect squares right here. But we can do something that can make our lives a little more efficient. So we're going to distribute this negative. So we have x minus 2 minus I for one of our factors. For the other factor, we're going to distribute the negative over here. We have x minus 2 plus I. Now we have our two factors. If you notice in our factors, there's an x minus 2 in both factors. If you regroup your parentheses so that you have x minus 2 here and x minus 2 here in your factors, you actually now have a situation where you have a difference of perfect squares. So my first term is in fact x minus 2 squared. And then my second is minus I squared. Now we have been working with a binomial product for a while. X minus 2 squared we can write as x minus 2 times x minus 2. And then, as you know, minus I squared is negative 1. So minus a negative 1. When we distribute this, we get x squared minus 4x plus 4. And then we have our minus a minus 1, which becomes positive 1. So when you completely simplify this, you have x squared minus 4x plus 5. Now, remember, the only way we got our difference of perfect squares is we distributed our negative. And when you distributed the negative, you were left with x minus 2 minus I. On the other factor, you're left with x minus 2 plus I. So this was our A, and this is our B. And so our A squared was x minus 2 squared. Our B squared was I squared. So that's where those terms came from if you were a little confused. Recall that we already learned to rationalize the denominator with radicals. You multiply by the radical conjugate. We learned this before Thanksgiving break. Use the difference of squares pattern to efficiently rationalize the binomial denominators. This is just to remind you to figure out what the radical conjugates are. So if you have a plus the square root of b, the conjugate would be a minus the square root of b. We'll use this in the next couple problems. If we want to rationalize the denominator in this problem, we must multiply the top and the bottom by the radical conjugate. So we have 3 plus root 2 in the numerator and 3 plus root 2 in the denominator. Now, we just learned how to multiply efficiently in the denominator. So this is a difference of perfect squares. So you have 3 squared minus root 2 squared in the denominator. In the numerator, you're still going to have to distribute. So you have 4 times 3, which is 12, and 4 times root 2, which is just 4 root 2. Now when we simplify the denominator, we have 3 squared, which is 9, minus root 2 squared, which is just 2. The numerator cannot be simplified anymore because you have a constant and a radical term. So in the denominator, we have 9 minus 2, which is just 7. This is as far as we can simplify this. Now, if you'd like to simplify it, you can simplify 12 over 7 plus 4 root 2 over 7. But you don't have to split up the fraction.